Okay, welcome. We are going to do every Fitch-style proof in this packet. Let's begin. I'm assuming a background for this video that you've already been introduced to the rules of natural deduction, and I'm not going to really make any kind of comment on that. I'm just going to go. You'll figure it out. Woo! Proof number one. I'm working from a particular packet that you may or may not have access to, but here's proof number one. Well, actually what I'll do is I'll write the argument. The argument is, we have one premise, A and B and C, and we want to conclude from this A and B and C. Okay, of course, this is true, or rather I should say, of course, this is a valid argument. And we can prove that this is a valid argument, and hence that this conjunction symbol is sort of associative in a kind of a sense. Okay, how are we going to do this? Using the rules for and introduction and elimination. So we begin. This is our first proof. So we have this vertical bar and this little horizontal bar, and we number our lines, and we put the premise above the little horizontal line. So that's the premise of our argument, and we need to work down to here. Okay, well, I think it's just clear what to do. We squeeze information out of this conjunction by decomposing this conjunction into the conjuncts, A and B or C. Reason is and elimination. It's a rule and elimination which tells us that sort of the power of a conjunction is that if you know a conjunction or have a conjunction or are sure that it's true, then you can assert the truth of the conjuncts. So applying that rule 2 times to decompose it, I'm now getting closer to what I want. I'll do one more thing, which is to decompose B and C into B and, might as well at the same time, get C. Reason and elim 3, and so I notate with the kind of a justification every line of my proof, except for the assumptions. Assumptions or premises don't get annotations because they don't need to be justified. Okay, here we are. Now, I want to show A and B and C, so I conjoin A and B together, and that is a rule called an intro, which says that if you know 2 propositions, then you can assert their conjunction. And so this is 2 and 4. And finally, I and together, cha-cha, I and together line 5, and I get the thing that I want, justification and intro. What did I say? 6, 5. Okay, good. Woo! Done. I think that was extremely straightforward and bordering on kind of just boring. Good. More. They get more interesting, I swear. But not so quickly. Here we go. Here's proof 2. This is going to exhibit some other some new properties or something like that. Okay. Well, what are we doing? Here is the argument. The argument is premise A and B, conclusion A or C and B or D. Okay. Well, if you think that out, you can convince yourself that that's surely true. Let's do the argument right now. This argument has one premise, A and B, and from this conjunction, we can break it down into its 2 conjuncts, and elim 1 and elim 1. But then we have a rule which says that if I know A, or rather if A is true, then A or C is true. This is sort of you can think of as kind of a weakening of the information in line 2, but it is certainly valid that the argument that I'm claiming is valid now is the argument that says if A, then A or C. This is a valid argument, and that itself, the validity of this argument can be checked sort of by brute force with the truth table. The truth table gives the semantics of these propositions. It tells you under precisely what conditions these propositions are true and false. And so by making a truth table, you can see that this argument is valid. The definition of validity is that whenever the premises are true, the conclusion is true. And if A is true, then by the definition of the or connective, A or C is true as well. So since this argument is valid, then that sort of is what justifies our rule. This is one way of looking at it. And the rule that I'm talking about is this rule called or intro. The rule, the sort of rule of logic that takes you from line 2 to line 4 says that you can just add a disjunction on to any proposition once you know that that proposition is true. Okay, so just to kind of repeat that one more time, the sort of understanding of what's going on here is that we have these rules that we're proposing for our Fitch-style proof system. Each of these rules can, well, I think they're also very, very intuitively clear, the rules, but if you want, the rules can themselves be justified as being sound, which is to say that the rules are truth-preserving, or that the rules produce valid arguments. And I didn't even bother doing it, but I talked it out. What I just did here is a sort of justification of the or intro rule. And so if the individual rules of our system are each produce valid arguments, then sort of repeated arbitrary applications of those rules will produce valid arguments. And that's just what a proof system is. It's a method for sort of generating valid arguments. Okay, and by limiting ourselves to some small number of basic rules, here we have 2 for each connective, we then sort of reduce the burden of justifying our valid arguments via truth tables down to a sort of small number of basic arguments, and more complex arguments can be justified by virtue of these rules. And this is sort of, to me, this is sort of doing logic. I think this is the point. When you're making truth tables, you're not really doing logic in a certain sense. This is really doing logic. You're constructing logical arguments, which was kind of the point of logic to begin with. Okay. Where was I going? Oh yeah, I'm going to or on a D to this B reason, or intro line 3. And finally, in rule 6, this says that A or C and B or D, and that is coming from the rule and intro line 4 and 5. And so we sort of win. So okay, the way these proofs work, if this is not sort of clear, I'll just make it explicit. I didn't really say all this, didn't go into this kind of level of detail in class. I took it as kind of, I don't know, obvious or something. But, you know, the proof goes in a kind of a linear fashion, and every single line of the proof is potentially a place where you could have stopped. And so if the goal was to show that this argument is valid, well, I have shown that this argument is valid. As long as we know that all these individual rules are valid, I've gone from 1 to line 6, and there it is. Okay, these 2 proofs were, you know, not that hard or interesting, sort of, or fun, but they just give you a kind of a gist of our system. When it really gets kind of interesting is when you sort of start expanding to logical arguments that require sort of more complex arguments. And here, okay, I'll just do it. This was proof number 3 in the packet. This was given sort of verbally as a, well, I'll say over here that we have these premises, M or F. F implies C, M implies C, and therefore C. Okay, and in the packet, this was kind of stylized as some sort of, this was a sort of a bad example that's very not bad, but kind of not interesting, or I should change it, but it was something like, either my mother or my father, is happy with me or something like that. If my father is happy with me, I'm going to get a car. If my mother is happy with me, I'm going to get a car. But since one of those must be true, then I'm going to get a car. Okay. Anyway, that's not important. What is important is that this argument here is sort of intuitively valid. Never mind what these propositional variables were supposed to represent. Taking this more abstractly, here we have this argument, and I claim this argument is valid. And showing that this argument is valid is, there's always the option available, which is to just make a gigantic truth table. In this case, it would be, we have 3 propositional variables, so this would require 8 rows of a truth table, and you could just could confirm that this is true, but of course no one reasons like that. The way they actually reason is by doing a kind of proof by cases. They say, okay, well, since one of these must be true, but each of these lead to C, then C must be the case. Okay, and let's do it. Yeah. This formal proof system that we are introducing, the Fitch-style proof system, is really Fitch-style is just the kind of style of indenting and kind of some naming and notational conventions, but the overall kind of proof this is what's called a proof, a natural deduction proof. And it's a natural deduction proof in the sense that it's supposed to model the way we actually reason. And the way that we actually reason is not by making a truth table. We don't know, no one would sort of confirm to themselves that this is a valid argument by constructing a gigantic truth table and checking every case. Instead, they just perform a proof by cases, as we have just done. And so we are creating a formal proof system which models that way of reasoning. So that's by natural deduction. So it's called natural. Okay, and so how do these natural deduction systems work? They involve, or how does this proof by cases work rather? If I have this disjunction, then what I need to do is I need to show that both of these cases leads to C. And I don't know, however, which one of these is true. I just know that the disjunction is true. I have line 1, so I know M or F is true, but I don't know which one of them it is, or it could be both. And so I have to now make a subsequent assumption, and that's what the idea behind this indentation is. We indent when we make another assumption, and there's this kind of echo of the horizontal bar which separates premises from the body of the argument. Because now every assumption is kind of like a new premise of a new mini argument, and so there's a kind of a fractal nature or something like that to this proof. Not fractal, but it's recursive in the sense that I now sort of start a new argument inside of my main argument. That's really the best way of thinking about it. All this kind of stuff that I do know how to teach this. It's just very time consuming to explain all this stuff out. So anyway, we are doing it by video. Then no one will watch. I assume M. Now I reach for this line 3, which says if M then C. And so I conclude C. Okay, this is called arrow elimination, and 3, 4, and arrow elimination is just the technical name for modus ponens. And okay, here, this some of the stuff I did say in class, but ultimately that rule, the rule arrow elimination, which I'm using for the first time in this video, can be thought of as sort of codifying this argument. And once again, this argument is valid. You can convince yourself it's valid by making a truth table, and once you've convinced yourself that it's valid, then it's a legitimate rule, and we're going to use this rule from now on. But sort of on a deeper level, this rule sort of explains, what even sort of conditionals are. What is a conditional? What is the sort of meaning or purpose or destiny of a conditional? And the answer is a conditional tells you that, well, if the antecedent is true, the conclusion is true. And so, one may, when given a conditional, if you also have the information that the antecedent holds, then you know that the conclusion holds. And so this is arrow elimination in the sense that we eliminate the arrow, we use the arrow, we squeeze information out of the arrow. Okay, and notice that C, I've reached sort of as my goal here, what was the overall goal of this proof, which was to conclude C. And so now I've shown, it just took me 2 lines, or 1 line you might say, that this M leads to C. Okay, and now I immediately begin with the other half of the proof by cases. So I knew that from line 1 that either M was true or F was true. So I assumed on the one hand M, I got the conclusion I wanted, and now I stop, note this break here, I stop that subproof has kind of ended, and I begin immediately after it another subproof, and now I get to also conclude C from this subproof, reason, arrow elim 2, 6. In other words, I have this conditional, if F then C, but I know F, therefore I conclude C. And so I've shown, looking at line 1, that M leads to C and also F leads to C. And so, and here's the key idea now, I dedent, that might even be a word, I unindent, and I go back down to the main body of my proof. I end the subproof. This was in fact sort of 2 back-to-back subproofs, each of which were linked, and I conclude C. And okay, intuitively, I'm entitled to that conclusion because I showed, by virtue of the subproofs in 4 through 5 and 6 through 7, that C is a consequence of line 1. And it is in fact the disjunction in line 1 which let me engage in this proof by cases. A proof by cases is an exploration of a particular disjunction, and so this rule, which is called OR elimination, is a way of squeezing information out of a disjunction. And the notation here is 1, you note the line number of the disjunct that we're eliminating, and then you list the line numbers of the subproofs, the back-to-back subproofs in which you explored that disjunction. And the formal nature of this rule says that you have to conclude each of these subproofs with the same conclusion. And if you reach the same conclusion in both subproofs, then you're entitled to assert that conclusion back in the main body. And you should think of line 8 as really being sort of the result of line 1. And that's the sense in which it's an OR elimination of line 1. We're eliminating this disjunction. We're eliminating the disjunction by using it, by exploring it, by squeezing information out of it. And in fact, this just is the way to use a disjunction. The only way a disjunction can possibly give you any kind of power, if I know, P or Q, the only way to explore that, to use that piece of information, is to sequentially explore each of the disjuncts. Since you know one of them must be true, if they both lead to the same path, then you can be sure that this line 8 must be true. Okay, all right, it's going very slow. But for someone who doesn't know anything, this is maybe the right approach. And for my own students, you're either not watching this at all, or you're watching this on 2 times speed, or maybe more. Now I think I have less to say, so I'm just going to do a bunch of these. So here we go. Here's an argument. The argument is B and A, or A and C, and if that's my premise, I conclude A. Okay, I want to show that this argument is valid. How? I'm going to do a Fitch-style proof. Let's go. So, line 1, I have B and A, or A and C. I think this is how I should have made this packet, actually. I should just sort of list at the top of every page an argument and have you show that it's valid. I think that's a better way of putting it. Maybe. I don't know. Anyway, we begin. This is the sort of goal. Up here, what should I do? Well, I have only a disjunct, so there's only really sort of one thing to do with a disjunct, and that is to do a proof by cases. And so what I'm going to do is indent, assume on the one hand B and A But, okay, now this just becomes silly, right? Because from B and A, of course, I know A, which is the only sort of relevant one to me at the moment. Reason and elim 2. But on the other hand, I end this subproof because I got what I wanted. On the other hand, I know, I assume A and C, the other disjunct, and from that, I conclude A, reason, and elim 4. And, okay, there it is, right? I looked at each disjunct. Both of them led to A. So I conclude A. Reason, or elimination. I began with a disjunction. That disjunction was line 1. I explored it first in lines 2 through 3, then in lines 4 through 5, and so I proved A. Okay, good. Woo! Let's keep going. Proof number 5. Oh yeah. Okay. Here we have premise P or Q and R, and from this we would like to conclude P or Q and P or R. Okay. Let's begin. My first line is P or Q and R. Let's see what I can do. Well, here, okay. Let's sort of just maybe start. I think this is actually still pretty easy because I have this thing that I'm trying to prove, and I have really only one thing to do now, which is a proof by cases. So I'll just begin my proof by cases. This is a disjunction. On the one hand, it might be the case that P is true. Well, does P entitle me to this conclusion? Yes, because I may or on this Q by or intro line 2. I can then or on R, and that's also or intro 2, and then I get P or Q and P or R, reason and intro 4, and that's what I wanted. So I showed that my left disjunct P does in fact imply this, which is just kind of makes complete sense if you think about it. Okay, well, what about the other possibility? What if it was Q and R that was true instead? Well, then I can still do this, right? Because I can get Q, and I can or P onto the front of Q. On the other hand, I can get R, and I can or R on, I can or a P onto the other side of R, and then I can AND them together. So P or Q and P or R. Okay, so here I didn't notate as I go, so I'll sort of explain myself now. This is and elim 6. This is or intro 7. So I just I weakened my line 7 by ORing it together with a P, and sure, you can put it up on the front like this because we want that kind of power, and it doesn't matter. Here we have this is also this line 9 also just comes from line 6. Once again, I sort of weaken my line 9 by ORing a P onto the front, and finally this line 11 is and. Oh, I guess I should squeeze it in here. Need a better board situation. And intro 8 and 10. Yeah. And, well, now I have finished my subproofs. I've showed that my left disjunct leads to my conclusion, and that my right disjunct leads to my conclusion. Thus, I just have my conclusion. And so you're not sort of done with the proof. This kind of goes without saying or something, but you're not done with the proof until the thing you're trying to prove is out at the most sort of dedented line, back at the main bar of the proof, so to speak, at the same line as the premise. I think that maybe goes without saying. Okay, what's the justification for this? It's an OR elimination, and the disjunction that I eliminated was the disjunction in line 1, and I did it via 2 subproofs. A subproof that went from line 2 to line 5, and a subproof that went from 6 to 11. Okay, so that one was maybe a little bit harder or something, but really not. Okay. Then come sort of 3 proofs that are bordering on, silly. Well, let's not disparage the proofs. Let's just do them. So that was proof 5. This is proof 6. What's proof 6? Well, this is really just more practice, right? The argument now is A and B, or C and D. And from this, I would like to conclude B or D. Okay, that seems pretty reasonable, actually very reasonable. Okay, so we begin. My premise, A and B, or C and D. Once again, the main connective in this proposition is or, so the overall, this line 1 is a disjunct. What I mean by main connective is this sort of the connective which is kind of syntactically, governing this sentence. What counts as a well-formed formula of propositional logic is defined recursively by applying the rules allowing you to add 2 propositions together with a connective in the middle, or wherever the connective is. So here, there's got to be some rule which says, hey, if you have a proposition X and you have a proposition Y, then X or Y is also a legitimate proposition. And so it's the sort of it's the last application in the recursive definition of what makes your formula syntactically well formed that determines sort of what you are. The main connective here is an or, and therefore you need to sort of kind of let your eyes glaze over the stuff inside the parentheses and just see line 1 for what it is. Line 1 is a disjunction. And if this is a disjunction, then we sort of have to do a proof by cases. It's the only way. So I indent here to begin a proof by cases, starting with A and B. But okay, if I know A and B, then I certainly know B, and then I certainly know B or D. Here, this is and elim 2, and this is or intro 3. Okay, then I will try the other disjunct, C and D. Well, from this, I conclude D, of course, and from that, I can or on a B. Okay, I'm now sort of pretty much done, right? This line 6 came from an and elim 5. This line 7 came from an or intro 6. I did a proof by cases now. Both of my disjuncts led to the same conclusion, and therefore that conclusion just holds. B or D. Just because my proposition in line 8 is a disjunction, the justification for this line 8 is disjunction elimination, because the justification for line 8 is that it was the result of a proof by cases. In other words, I began with line 1, I eliminated that disjunction in line 1 by virtue of conducting the proof by cases on that disjunction. And I did that via the subproof 2 through 4 and the subproof 5 through 7. Okay, we're just gonna keep going. Yeah. Seven. Proof number 7 says, all right, take this premise B and A, or A. Hope I haven't changed this packet at all. I think this is still proof 7. And from this, I'd like to conclude A. Is this argument valid? Oh, of course it is. Come on. Either B and A, so A, or just A, so A. But there's actually a nice opportunity here to learn something. Well, there's one sort of feature of our system which you're about to be exposed to. So B and A or A. Okay, well, I have a disjunction, of course, so I need to do a proof by cases. So I just begin that proof by cases kind of without delay. So I have B and A. And, all right, it seems I'm done because there's just A, right? So reason and elim line 2. All right, so far so good. And now the sort of nature of our proof system is that I consider the other case being A. But now I see that like I already, even just in the premise, have the thing that I want. All right, so okay, you know, you could argue about this kind of thing, but you know, the sort of the formal nature of this proof system requires that you stick to a certain precise syntax. I'm talking about the syntax of the proof itself. And here the syntax of the proof itself is that these two things here, line 2 and 4, need to be the disjuncts that you're exploring, and each of these subproofs need to conclude with some kind of line here. And so it is for that nature that I really do want to sort of rewrite that A like that. So there's a rule for this. It's called reiteration. And I think I mentioned this as maybe the very first rule of this proof system in class I did. And you might have thought, why would I ever want to just like restate something for no particular reason? Well, sometimes you need to kind of force your your proof to be in a certain format in order for the proof to be correct according to the rules we've set up. And this is one of those cases. So I just sort of repeat line 4, therefore I can say that line A holds. I just really needed both conclusions of each case to end in the same exact kind of way like that. Okay, and where did this come from? This is an OR elimination. I started in line 1 and I did 2 through 3, 4 through 5. Oh, we got a crying baby, but he's gonna just cry because I'm doing 3 more proofs. Yeah. Proof 8. Woo. Is quite short. Not even sure why this is on here. The argument says, dude, if you know P and Q, you can certainly conclude P or Q. Okay, this is just simple proof. We have P and Q. From this, I conclude, I guess there's a bunch of ways of doing this. I guess I can conclude P. I might have cut this proof out. I can't remember. Anyway, so from that I conclude P, and that reason and elim 1, and then I conclude P or Q, reason or intro 2. Okay, 2 more. 2 more. Let's do it. I think I can squeeze them both over here on this board. There is proof 9, which says, okay, I have 2 premises, A, B, or C, and from those 2 premises I would like to conclude A and B, or A and C. Alright. Well, that seems pretty reasonable if you think about it. Let's not think about it too much. Let's just begin. Line 1A, line 2 B or C. What am I going to do? Well, I have to use line 2 somehow, and there's only one way to use line 2, and that's to do a proof by cases. So let's do that proof by cases now. I assume the left disjunct B. Oh, okay, well I also have line 1, right? So line 1 says that if I now have A and B, then I have A and B, reason and intro, 1 and 3. But of course, this is pretty close to the thing I'm trying to prove, because the thing I'm trying to prove is a weaker version of that. And so I say A and B, or A and C. And, okay, reason, or intro 4. Okay, and that concludes my left disjunct. Now we go to the right disjunct, which is C. And, yeah. So if on the other hand C, then I can make A and C by and intro 1 and 6, and then that line 7 is pretty close to my conclusion. My conclusion is just a weaker version of that. So I OR on this thing to the front of it. Yeah. And that is OR intro line 7. And I did indeed hit the same spot in both of my subproofs, and so I may now assert back on the main line A and B or A and C. Reason, or elim, line 2, 3 through 5, 6 through 8. Okay, good. Last proof. Proof number 10. This is what it says. I have a premise. The premise is A and B or C. And from this, I would like to conclude C or B. Okay, this one's kind of maybe a little bit nice. So let's go. My one premise is A and B or C. And well, once again, the main connective is a disjunction, so there's only really one way to do this, which is to do a proof by cases. So this is A and B. Okay. Well, my goal is C or B, so keeping that in mind, from this I can get B, reason, and elim 2. Just comes directly from line 2. And now I can just OR a C on to the front of that B. Reason or intro 3. Okay, that concludes that subproof. What about the other option, that it was C that was true, the right disjunct? Well, now it's even sort of simpler to just OR on that B. So that's OR intro 5. And here I have concluded C or B, so back out at the main body of the proof, I now know C or B. Reason, or elim, in other words, I started with line 1, yeah, sorry, zone out for a second, or elim 1, 2 through 4, 5 through 6. Okay, there it is. This is a this is me doing all of proofs 1 through 10, but also kind of making this video sort of appropriate to an audience who even maybe didn't have the packet and wasn't even there for the lesson on what the whole point of all this was. So hopefully this was helpful for whoever is watching it. This is we are in no way complete. We have done the first 10 proofs of this very large packet. And we've seen some of the rules, but not all of the rules. We will sort of introduce the rules kind of as we go. I will in these videos. But we've seen proof by cases, and we have sort of proof by contradiction and conditional proof to go as the two other big sort of proof techniques that involve subproofs. But this is a pretty good introduction to how this Fitch-style proof system uses. Or how it implements proof by cases. Okay, good. These were the problems that were due like Friday or something. So because we didn't go over them in class because we have no time, I'll tell everyone to watch this video, and then I'm just going to make videos for the rest of the problems as well. Goodbye.